AP Calculus AB. This is going to be Unit 6, Day 6. This is our notes. So this is a handout you should have or you can print out. And we're going to use to kind of just go through some solving differential equations stuff that is review. So let's take a look at it. And we'll just kind of read through it and we'll add some stuff for sure. So people often think that to find solutions of differential equations, you simply find an antiderivative, then use the initial condition to evaluate the constant plus e. While this gives you the start to find solutions of initial value problems, consideration must also be given to the domain of your final result. Sometimes these considerations are obvious, as an AB 6 from the 2000 AB exam. Sometimes it's obvious. Sometimes it's more complicated. So let's why don't we try this one ourselves? Let's see if we can solve this differential equation. There's gonna be a bunch of these in our next test, so it's just good practice, anyways. So we want to, maybe pause the video if you feel confident in doing it. You want to separate the variables, and then integrate both sides. If you're having to wait for me to do this, then I'm a little worried because I've already been reminding you how to do this even in this unit. Antiderivative e to the 2y is e to the 2y, but you're going to get extra 2, so you got to divide by 2 equals 3x cubed over 3 plus c. We have an initial condition. I'd find it right now. So it's going to be e to the 2 times the y value is 1/2. So c equals e over 2. So if we rewrite it, e to the 2y over 2 equals x cubed plus e over 2. Now I would multiply both sides by 2. And then we get e to the 2y equals 2x cubed plus e. And then we're going to take the natural log of both sides. And can't do anything there. Can't simplify that. Cannot break that up. Divide both sides by 2. And we get y equals 1/2 natural log of 2x cubed plus e. Okay, so they kind of talk about it right here. They kind of go through these steps. The requirement, okay, says the requirement that 2x cubed plus e greater than 0 or equivalently x is greater than negative e over 2 to the 1/3 power is a natural condition to have the logarithm function defined, so it includes initial value and avoids the singularity. Singularity is where it's not defined. So, they're saying, hey, obviously, this is your solution, but the inside of this, the domain of your answer, this has to be positive. Divide by 2, it's negative. And you're going to take the cube root of both sides. So the negative pops out. This is the domain, right? So, you could say this is, this is sort of the basic domain, but then when we solve it, this is the domain. And they're saying it's obvious just because that's the domain of your answer. Like if I ask for the domain, that's the domain. However, finding solutions of initial value problems for separable differential equations need not always be as straightforward, as we see in the following 4 examples. So this was kind of an easier one. These ones are going to have some other issues we've got to watch out for. So let's see if we can go ahead and solve it just on our own. They kind of walk through it, but let's see if we just do it on our own. Let's separate the variables, which is actually pretty easy this time because there's no y's. Integrate both sides. Natural log of x plus c. Use the initial condition. Natural log of 1 is 0, so c equals 2. We rewrite it, y equals natural log of the absolute value of x plus 2. So that's our solution. Now, as far as domain issues, X has, well, X doesn't have to be greater than 0 because the absolute values. X cannot equal 0. That's the one condition. X cannot equal 0. It's vertical asymptote. But this is, so let's see. So I mean, the domain of this would be negative infinity to 0 and 0 to positive infinity. If I just gave you this function, you would tell me that was the domain, but that's not what we're going to include here. Okay, so it says, however, even though this function satisfies the differential equation, the initial condition is not the solution of this differential equation. The solution is this. This is what they're saying the solution is. The reason for this is that the usual definition of the solution of a differential equation is that of a differentiable function on an open interval that contains the initial value. This is the key thing right here. The solution, the usual definition of solution of differential equation is that of a differentiable function on an open interval that contains the initial value, and open interval 1. Notice that the function in 1 is also defined for x greater than 0, while our solution must be continuous on an open interval containing the initial value. Thus, the domain of our solution cannot contain x equals 0 or positive values, but must include negative 1. That was the initial condition that we were given. This requires the domain to be an open interval. So, this is going back to what we're going to do. Usually what I would do is I would do kind of a line check, and I'd put any places where this was undefined, or even the derivative. If you look over here, x cannot equal 0 because then the derivative is undefined. And I mean, here just coincidentally, it's happening in the same place. But sometimes this gives you a new spot that this doesn't. Now, we're not going to test values. We're just going to look for the initial condition, negative 1, x equals negative 1, identify where it's at, and this is the side, single open interval. Open meaning we can never contain the edges. So the domain is just going to be negative infinity to 0. Even though this function on its own does have answers over here, they're saying as a solution to this differential equation, it must be a single open interval that contains the initial condition. Okay. Now, with that in mind, any answer to a solution of a differential equation that involves absolute values is definitely going to be broken up, and only 1/2 is going to be used. So we know we're plugging negative numbers in here. So the best answer is to drop the absolute values, force the inside to become positive. We know it's going to be negative, so an extra negative is going to do the same thing as an absolute value for the domain negative infinity to 0. This is the best answer. Okay? All right. So, and this is the initial condition, right? That's why we picked that side instead of the other side. If the initial condition was positive 1, we'd choose this side for our domain, and our answer would look different. It'd just be natural log x without absolute values. Okay. As a second example where we need to be careful, consider the initial value problem. Okay, let's see if we can go ahead and just solve it on our own. Now, it's hard to see, but there's a negative right there. So I'm going to just rewrite this a little more friendly. This is the same thing as 1/3y squared. Okay, so we're going to separate the variables. I'm going to go and just bring the 3 to the left, just because I see how nicely it's going to work out when I integrate it. You don't have to. You can leave the 1/3 on the right. And so we're going to get 3y. Oh, actually, it's not going to work out that great. Oh, yeah, no, it's y squared. It's going to be 3y cubed over 3 equals x plus c. And 3's cancel out. We use initial value to find the c value right now. So we're going to plug 1 in. And so then c equals 0. So then we're going to rewrite it. It's going to be y cubed equals x. We're going to take the cube root of both sides. no plus or minus. So y equals the cube root of x. Okay, and then we need to consider domain. Now the domain for this is all real values. You can plug anything in you want to an odd root. Okay, so you might think, oh, well, that's a domain. Now that's the straightforward domain, but the derivative has to be defined. And right here, dy dx equals 1 over 3 y squared is going to be undefined when y equals 0. Now, y is a range thing. Domain is supposed to be x's, so we're not going to break up our domain at 0. This is the y value. We need to figure out, well, what's the x value? This cannot happen. So we just solve for y in terms of x. So this can't be 0, which means that x can't be 0. So what I'm going to do is I'm going to do a line. I'm going to put open dot at any issue. And I'm not going to do any tests or anything like that. I'm just going to pick the side where the initial value was, the x value. This is our domain. So our final answer is going to be y equals the cube root of x for the domain 0 to positive infinity. That's our answer. Okay. So, and that's just in these cases where this solution came from that differential equation. It has to come, that has to exist. Anywhere this doesn't exist, it doesn't make sense to say there's an answer that you got from something that didn't exist. And we have to break it up. It's only valid for the chunk that the initial condition is on. Okay. So, I don't know if we want to emphasize that, maybe we should write that right now. Domain for these guys, domain is an open interval, okay, single open interval where the function is defined and the differential equation is defined. It's not enough for your answer to be defined. The derivative has to be defined too. And contains the initial condition. This is what these are the requirements for the domain of the solution of a differential equation. Okay. All right. Got a couple more examples to really take this point home. Okay, so for another example where we need limit of the domain solution. Okay, so let's separate the variables. Dy over the square root of 1 minus y squared equals dx. We're going to integrate both sides. Okay. Now this right here, I don't know if you recognize it, this is inverse sine of y equals x plus c. And then if we plug in the initial condition, this is asking you, what angle do you plug in a sine to get 0? Well, that would be 0, principal values. So c equals -1. So we get inverse sine of y equals x minus 1. And then to undo inverse sine, to get y, you take the sine of both sides, because that would be the inverse function, right? Take the sine of both sides. So y equals sine of x minus 1. So that's our solution. Now, let's see. From our original differential equation, the slope field in figure 1 below, we see that our solution should never have a negative value for its derivative, whereas our solution in 6 is oscillatory. The problem occurred when we solved the equation 5 for y equals x. In 6, we needed to limit the domain of our solution to an interval of length that includes our initial value and on which the initial sign graph is increasing. So let's see what they mean here. Okay, our solution, okay, this goes, I think, back to this. Okay, this has a domain of all reals. This right here on its own, domain is all reals. Okay, but in the original, we see that 1 minus y squared has to be positive or equal to 0. Okay, so that means if we factor this as 1 minus y, 1 plus y, greater than or equals 0, y equals 1, y equals negative 1. But we need to, and we could do like a line check and stuff, but really these are actually easier than that. These are going to definitely break up the domain, but we got to find the x's that go with those. So what values are those going to be? And I mean, if we were to solve this, it would be y squared is greater than or equal to 1. And that would be y is bigger than negative 1 or less than, or actually, hold on. Now, we would, if we move the negative over here and we divide both sides by negative, it would flip the sign. So then y squared is less than 1. That means that y is between negative 1 and 1. That's the range. And that's what they're saying up here, is that our answer can only exist here. Okay. Now, trying to find the x values that go with these. Okay. So it says the slope field, we see that our solution should never have a negative value, okay, for its derivative. All these slopes are positive, right? Can never be negative. I mean, that's one issue here. There's no way this is ever going to be negative. It's square root of something. So we got to limit the domain in here so that we never get any negative slopes. Because if you look at the sine curve, it goes like this, right? And then you start getting negative slopes, which our derivative up at the top says isn't possible. I'm just trying to explain this, okay? So now that we figured this out, let's figure out what the let's figure out the x's that would go with this. So if you set y equal to 1, say, well, y can't be 1, right? It's actually be an open dot. You're saying, okay, well, when does sine equal 1? Well, sine equals 1 at pi over 2 plus 2 pi k, right? So then x equals pi over 2 plus 1 plus 2 pi k. That's one of those spots. And then negative 1. When does sine equal negative 1? Well, that happens at 3 pi over 2 plus 2 pi k. And then we could solve that and be x equals sine 3 pi over 2 plus 1 plus 2 pi k. Now, there are infinite values then that we're going to break it up. But I would just do a line check. I'd say, okay, let's do a line check. Let's put, pi over 2 plus 1 on here. Let's put 3 pi over 2 plus 1 on here. And then there's going to be more, right? They'll keep going. This one, if you subtract 2 pi from this, you get negative pi over 2 plus 1. If you add 2 pi to this, you would get 5 pi over 2 plus 1. So anyways, we could keep this going. But we only want the one where our initial condition, x equals 1. Now this is like a 3.14. This is like 2.5-ish, right? This one's like 4.5, like 5.5. This one is like negative 0.5. So x equals 1, I think, would have to be in this chunk right here, right? So our domain is going to be negative pi over 2 plus 1, comma, positive pi over 2 plus 1. Open interval. So our final answer, y equals sine of x plus 1, which didn't have any domain issues, but because of the whole derivative that this came from, we have to restrict the values. Okay. So, and we don't include these because derivatives are two-side issues. So at the edges, we can't include them. Okay. Let's see. I guess we could look at one more here. This final example illustrates the need to limit the domain of the antiderivative in order to have a solution of a differential equation. So here's another one. We're going to separate the variables. Integrate both sides. I'm going to rewrite this as y plus 2 to the negative 3 halves. Right? It's a power rule. So the antiderivative is going to be y plus 2. We're going to add 1. It's going to be negative 1 half. Divide by the new exponent. Equals x plus c. I'm going to rewrite this as negative 2 over the square root of y plus 2 equals x plus c. I'm going to use the initial condition. Plug in negative 1 in for y. Plug in 0 for x. That's going to be 1. C is going to equal negative 2. All right, so then we could rewrite this as negative 2 over the square root of y plus 2 equals x minus 2. Now, I'm going to flip both sides. And I'm going to multiply by negative 2. And then I'm going to square both sides. And I mean, you could leave the negative 2 in there, but the top is getting squared and the bottom is getting squared. And then we could subtract 2 from both sides. Lots of algebra here, right? So y equals 4 over x minus 2 squared minus 2. Now, domain-wise, x cannot equal 2 just from this guy, vertical asymptote, okay? But we have another issue also. We gotta look up here at our derivative and say, okay, well, this is dy dx. This is the square root of y plus 2 cubed. So y plus 2 has to be greater than or equal to 0. Which means that y has to be greater than or equal to negative 2. Okay, but we got to find the x value that makes that happen. So we can go back to our solution and plug negative 2 in for the y value and figure out what the x is that makes that happen. So we add 2 to both sides. I mean, we could try and cross multiply. If you cross multiply, you get 0 equals 4, which is just not possible. Which means there's no way for this to be, there's no way for y to equal negative 2. It can't happen. There's no x that makes that happen. So I guess we don't need to worry about it. So I'm going to do a line check with this 2 value here, put an open dot. Our initial condition is at 0. And so that's going to be our domain. So our final answer is y equals 4 over x minus 2 squared minus 2 for the domain negative infinity to 2. That's our final answer. Okay, now let's just read what they say. We notice that 8, right here, the solution, the same as what we got, is valid for all x not equal to 2, and that this solution will have negative slopes when x is greater than 2. This is going to end up being negative. Okay? While our original differential equation requires non-negative slopes everywhere. There's no way that this will ever be negative. Okay? It can't be negative. Square root of something cubed will never be negative. And so they're pointing out, hey, this is why we got to break this up. This is why we can't plug the numbers in over here, all right? a look at the slope field in figure 2 all below demonstrates this fact. So here's the slope field. It never has negative slopes. Okay. We got into this trouble when we squared both sides of 7 to obtain our explicit solution. Because the left side of 7 is always negative, we must limit the right side to x plus c is less than 0. Thus, we need to add the condition to our solution in 8. Notice that we could not consider x greater than 2 in any case, since the domain must be an open interval containing our initial condition and not include x equals 2, where the solution is not defined anyways. This example shows that we may not extend a solution across a discontinuity, even if the resulting function formally satisfies the differential equation on the other side of the discontinuity. We can't go through that discontinuity. We have to break it up. All right, so here's the conclusion. So what can we conclude from these examples? The process of obtaining an explicit solution from an implicit solution may result in an incorrect solution of our initial condition. We might get an answer that actually violates it. Okay? There may be values of x where the derivative of the explicit solution does not exist, even though it formally satisfies the differential equation. If you take the derivative of what we got, you're going to get back to what we had, is what they're saying. And just because that happens, that's not good enough. To avoid these mistakes, we can always check to make sure that the explicit solution is such that for all parts of the domain, the derivative of the explicit solution does not contradict the original differential equation. The original differential equation, original derivative, is important. Comparing the slope field for a differential equation with the graph of the explicit solution will display any differences. Its derivative exists for all values in its domain. So that was sort of a more in-depth reason, more in-depth inspection as to why the domain of solutions of differential equations matters, why we have to break it up, why we break it up, and why we do what we do. Now that you understand that, though, I kind of think it's not that bad. It's easier than finding the domain of the answer a lot of times, because usually you'd have to do line checks and find multiple sections, multiple intervals. But now we know we just got to pick that one where the initial condition lies. So today's assignment, you're going to try some more on your own. And here's just sort of a summary of what we just talked about. There's going to be a bunch of these on your next test.